Hello, so you need to be able to do the cardiac cycle, and there's two parts to it. The part that you knew at GCSE and just need a reminder of, and the second part which is harder that you possibly didn't do. So I'm going to recap very quickly what you did at GCSE. Now the first thing to note is this is a filled in diagram. On the PowerPoint there's an empty one. The reason why I put an empty one on the PowerPoint is simply because you have to include a picture of the labour diagram of the heart as part of your coursework. I don't expect you to draw that, but I do expect you to do the labels yourself, so you can't get it off the internet. So what I recommend you do is to take this as a blank one and then fill in the answers yourself, which I have done on this one for you. So just so it looks like to the examiner you've labelled it rather than just taking it from the internet. So the cardiac cycle is basically two things: thinking about the heartbeats, which we'll talk about later, and also the first and easiest thing is talking about kind of the flow of blood. Where is it going and why is it going there? So we start off at the vena cava, which is the vein that comes in from the body carrying deoxygenated blood. Blood comes in through the vena cava, fills up this area called the right atrium. Once that's full of blood, the atrium, the white bits on this diagram represent muscles. So those muscles squeeze and contract and push the blood through the atrium valves into the right ventricle. So these are called atrioventricular valves. Remember, the valves make it a one-way system, so it means that once the blood has gone from the atrium to the ventricles, it can't go back. Once the ventricle is then full, the white muscle around the outside of this again squeezes and the blood shoots up through this way, out some more valves and up out of the pulmonary artery. Now pulmonary means lung, artery means it's going away from the heart. So this artery takes the blood out of the heart to the lungs. The reason for that is it needs to pick up oxygen to become oxygenated. So let's say the blood's up here now, picking up oxygen from the lungs, and then it comes back into this side of the heart through the pulmonary vein. Pulmonary meaning lung, vein meaning it's coming into the heart. So this blood is now oxygenated. It fills the left atrium, and once that's full again, the heart is going to squeeze, push the blood through the atrioventricular valves into the left ventricle. And once that left ventricle is filled, again the muscle is going to squeeze, the blood's going to come up and out through the valves out of the aorta. Now aorta is the main artery coming out of your heart. It takes the blood out of your heart and around your entire body and that's how the body gets oxygen. Now realistically both of these sides are happening at the same time with different blood, so this is kind of what's going on. It's doing that all the time. That is the cardiac cycle. So what I suggest at this point, you pause the video, write that down step by step. I'm in fact going to pause my video as well and kind of get a PowerPoint up to show you at the same time. So again, on the PowerPoint, that's what you have just seen. We've just gone through the cardiac cycle and the flow of blood. Something to hinder is the right and left hand side. This is because it's because as you're looking at the heart. So if this heart was on your body, you can do that by kind of picking up the computer and turning it around. That's what side it would be. So even though it looks like it's on the left, it's actually the right side of the heart. There is a slide here. I'm not going to go through it. It's just some more details about the cardiac cycle to help you. Right. The new piece of information that you need to learn is about something called the SAN, or the sinoatrial node. It's what we call our natural pacemaker. So it sets the pace that our heart beats at. It's made of specialized muscle cells that sit in the right atrium. So if we look at this diagram, the sinoatrial node is going to be about here. Oh, I've just drawn on the computer screen. That's better. Anyway, sinoatrial node is going to sit about here, and it's a specialised muscle cell that basically sends electrical impulses through the atrial walls to cause them to contract. So it kind of looks like this. So the best way I can think to describe it, okay, if we go back to here, is we said at the beginning the blood comes in through the vena cava, and when that atrium is full, okay, here's the sinoatrial node. What it will do is it will release an electrical impulse or an axion potential which will spread down these muscles, causing them to contract and therefore squeeze the blood out here. You then get to this point here where you have another node. So this is the sinoatrial node. The node here is called the atrioventricular node. So once the blood's been squeezed out, that electrical impulse actually hits that node and causes it to set off. So it then sends an electrical impulse around these sides and squeezes and pushes the blood out. That is complicated enough, and it's a really hard thing to understand on video, so I think you need to listen to that a couple of times. Here's just a different heart diagram which is trying to represent that. There's the sinoatrial node, it squeezes, it sends those arrows being the electrical impulses or action potentials across the top of the heart, making it contract, which pushes the blood down into the bottom parts of the heart. You then here, well, that's a bit lopsided, have the atrioventricular node, which again is going to come around and squeeze and push that blood up and out of the heart. So we say that the SAN, or the sinoatrial node, activates the AVN, the atrioventricular node. It says AVN generates own impulse down bundle of His. Now the bundle of His is just that middle bit there. That's what that's called. Now we can look at a heart scan on an electrocardiogram. That's basically what it would look like, and this is just all the different waves that would come out of the different parts of the cycle. You don't really need to worry about that. Now, how do we link it to the nervous system? And now this comes down to one of those paragraphs saying how they're all connected. Now, number one, we're talking about action potentials here. So there's a link that action potentials are being released by the SAN. However, the SAN is interesting because it doesn't need a stimulus to keep working and keep saying it. It constantly sends it. So we're thinking about how does it connect? Now we're thinking about when our environment changes and therefore we need to respond to it. So for example, the SAN will release an impulse just under every 1 second on average. Now that is your heart rate. Every time it releases an impulse, that is a heartbeat. So on average, most people have about 70 heartbeats in 1 minute. So just under every 1 second, you would feel your SAN would release that impulse and cause your heartbeat. Okay, now in some situations you need to increase your heartbeat. So for example, when you're exercising or you're in a fight or flight situation, your heartbeat will go up, and the reason for that is you need to be able to get oxygen around your body faster, in which case a message will come from your central nervous system to the SAN saying you need to release those action potentials or those electrical impulses at closer intervals. So like 0.5 seconds instead of every 0.8 seconds. Alternatively, we don't want our heart rate to be raised forever. We don't want it to go up and never come back down. So when you stop exercising, again, your central nervous system is going to send a message through the parasympathetic nervous system to your SAN saying, you need to slow down now. Now, this also relates to the stimulus response chains. So I've kind of drawn one out and I'm going to try my best to show it to you. I'm not very good with the camera work here. Apparently I'm just accidentally giving you a tour of my bedroom as well. Great. So looking at the stimulus response change, we talked about the stimulus being a change in the internal or external virus. We said that's detected by the receptor. The receptor sends a message down a sensory neuron from the receptor to the central nervous system. We said that could be the brain or the spinal cord. That then sends a message out through a motor neuron to an effector cell. An effector cell is something that's going to bring about a response, and the response will happen. So in black there, we've got the general stimulus response chain. Now let's liken that to the heart system. So for example, let's say you're exercising. The stimulus is your blood has an increased volume of CO2 and a decreased volume of O2 in your blood. So basically you have too much carbon dioxide and not enough oxygen. We need to get that blood pumping back to the lungs as quickly as possible. So the receptor that detects this are chemoreceptors. Remember, they detect chemicals in the blood, so they can detect that there's too much carbon dioxide there. A sensory neuron then carries this message to your brain. Now, when we're in the central nervous and we're in the brain, there is a place called the cardiac control center, and that's in a place called the medulla oblongata. Now, you just need to know that and write it literally as it says. That's just a very specific part of the brain. Okay, the medulla oblongata then sends a message down a sympathetic motor neuron. that goes to the SAN, and the SAN is stimulated. It tells the SAN to beat faster, basically, and in turn the heart rate increases. Now once you finish exercising, the stimulus will be there's a decreased level of O2 and an increased level of O2 in the blood. The app will be detected in the same place. It will go down a sensory neuron. It will go to the same place here, but here is where the change will be. It will be a parasympathetic motor neuron. The SAM will be stimulated and the heart rate will decrease. So there's just 2 E's there. I'm going to take a picture of that in a minute and I'm going to put that in the OneNote, but that hopefully helps you to go back to those stimulus response change, and some of you have already had that as feedback to go and correct one of those. Any questions, please let me know.